Hi, welcome to the next episode of our new educational video series on design and development of a wireless strain gauge. During this video series, we will define the principles of a strain gauge that have a wide range of application in the construction industry. My name is Farid, one of the research associates here at the Institute. In this episode, we will be covering the following topics. What is a strain gauge? Where is it used? What are the electrical principles behind any strain gauge? What is a Wheatstone bridge? And eventually, what conceptual designs are we planning to um, form? Firstly, as to the answer to what is a strain gauge, also known as a load cell in some contexts, a strain gauge is an instrument that converts deformation into electrical signals which can again be converted into load values measured in kilonewton, kilogram, or any other relevant units. In the construction industry, it has a wide range of applications, specifically in off-site manufacturing plants, factories, or anywhere that weighing plays an important role. Namely in batching plants for weighing up materials, cement silos in logistics, and health monitoring systems as well. So imagine a structural element that is constantly under huge loads, and you would like to have live data on this particular structural element. That is when strain gauges come into effect. Now let's dive into the electrical principles behind the strain gauge. In technical terms, a strain gauge is composed of a long conductive material with a certain resistance. It can easily deform to adapt to external forces and deformations. But how can we read the deformation and convert it into electrical signals? The answer lies in the formulation of electrical resistance. The electrical resistance of a given material is ρ times L over A. That is the specific resistivity, which is ρ, multiplied by the length divided by the cross-sectional area. And it is the reciprocal of conductivity. So in this slide, R stands for electrical resistivity and G stands for conductivity. So imagine a long wire under tensile stress. As it elongates, the cross-sectional area gets smaller, therefore the resistance increases. And the other way around on the compression, cross-sectional area increases, therefore resistance drops. Now that we know how to convert the deformation to an electrical signal, we need to know how to convert it into a load value, typically represented in kilonewton and other relevant um, units. For that, a circuit called Wheatstone bridge is used. The unknown resistance Rx, which also can be called the strain gauge resistance, is to be measured. Resistance R1, R2, and R3 are known, where R2 is adjustable. When the measured voltage Vg is zero, both legs have equal voltage ratios. So R2 over R1 would equal Rx over R3. So by adjusting R2, we can let Vg become zero. And the principle will be converting the load value into the known resistance. So for example, if we load the strain gauge by 5 kilogram load, we may get a resistance of say zero point 0.1 amps. When the load value increases, the resistance will change as well, and we are forming a linear relation between every reading. So next time when the strain gauge gets loaded by another way, by another load, we can predict the resistance and format our formula. The conceptual design of this video series is a wireless load cell that can measure and display changes in tensile stresses or compressive stresses in a structural element. The requirements would be a reliable power source because everything is wireless. So we need that power source to be carried out with our instrument. Ease of access for maintenance. So anytime you wanted to change that battery, you want to make sure that it is accessible. And durability is also another important factor because um, the less number of maintenance requires, the more convenience it will provide for the crew, and the impact resistance as well. We are going to deal with a large number of loads, therefore, it has to be impact proof, let's say, not to get damaged.